Hello everyone, welcome back to the next section on our Trig lecture video. I hope you've been able to solve the first problem of the day. You got a clue to the question, and so I believe you've been able to solve it. I'm hoping to make this lecture video as quick as I can, but let's see what happens. So we move on to the trig identities. With the trig identities, we have 5 common types of identity we are going to employ in our lectures. One is the quotient. When you hear the word quotient, you know something comes to mind. It is something over something that gives you a quotient. Reciprocal means 1 over something. So if I'm using the angles here, I'm referring to them as theta. So angle 1 over angle 2. Reciprocal is 1 over some angle. Pythagorean identities are also there. Now when you hear the word compound, Pythagoreans add up to a unit, so there would always be 1 in it. Compound means you are adding up the angles, so it would always come in addition. Take note. There's also half. Half means you're taking half of the angle, so it's going to be the theta over 2. That is how the angles will be expressed. And then when you hear of double angles, what should come to mind is twice of the angle theta. The double might look like the compound, but then because I know when I add, if theta 1 is equal to theta 2, then I can say I have 2 of this theta. But in this case, they are different. They are not the same. So we can say theta 1 plus theta 2, but the double is of the same angle, and so twice of that angle. These are the smart things that should come to mind. And so let's quickly go through the identities. Bear in mind that these identities you see on my slide are not magic. There are ways to prove them, but we are taking ourselves as end users of the proofs. So we just want to use the identities to solve problems. If you are interested to know how these are, there are so many documents you can go through for that. So bear with me. Look at the quotient rules. There are 2 forms of it. Quotient, I told you, is something over something. The common quotient identity we can never forget is tan theta. Trust me, from SHS we've known tan theta as sine over cos. We can never forget that. You may forget the cot, but tan theta, never. If you look at the reciprocal, we know this by offhand. It is the inverse of the functions. What's the inverse of sine? What's the inverse of cos? What's the inverse of tan? Another interesting identity we can never forget is this guy here. Another Pythagorean identity. Sine square theta plus cos square theta equals 1. We always rattle this, so you can never forget this identity. They come handy when it comes to these 3 guys here. Okay, but it doesn't mean you should forget the others. I'm just saying these are things we remember. And let's take a clue at the compound angle. Compound means we are adding some things. I want to make it quick for you and smart. If I'm adding 2 angles and I'm using the sine, you can compare what I have on slide 11 and what I'm doing in my write-up. What just happened? Okay, for sine, if I have plus and then minus, the resulting function goes with the same plus and minus. It means plus will give me plus and then minus will give me minus. If I have cos, plus will give you minus and then minus will give you plus. That is what it means here. The same thing for tan. Tan is a bit funny. In the numerator, the plus gives you plus, the minus gives you minus. But when it comes to the denominator, plus produces minus and then minus produces the plus. so it changes position. I'm not so sure if this looks smart for you, but you can find your own way of getting this at your fingertips. Aside the interchange of the signs, you want to see how these are computed. When it comes to sign, it says first let me have my sine 1, and then cos come and take the second one. So sine takes the first theta 1 and cos will take theta 2. When I move to the second term, now I let cos take the first and then sine take the second term. As simple as that. With the compound on cos, it says, hey, don't worry, I want to maintain myself. So my cos will take theta 1, the same cos take theta 2. And then I give the next component or the next term to the sines. So sines come in and say, okay, I also take the 1 and then 2. See the difference in the sine and then the cos compound. For sine, it patches with the cos, but for cos, it deals on its own and then give the rest to the sine component. I hope that is well understood. For the tan, I wouldn't go there because it's a whole expression on its own. So you want to keep these things in mind. Okay, so let me quickly take you through examples on how to apply this identities. Bear in mind this quadrant, they come in handy when you're expressing angles. Okay, so the first example, I always tell you extract information and then you ask yourself, what am I asked to solve? We are given some t ratios, 30 degrees, 45 degrees, and we are asked to find sine 75. Again, I know you can use your calculator to just punch this guy and then you have your answer. But how do we use identities? Because I'm giving two t ratios, it means I have to make use of them. If it's not important, it wouldn't be stated in the problem. And so realize that sine 75 can be evaluated or can be expressed as sine 30 plus 45. That gives me 75. Then you ask yourself, I have gone through quotient identity, I have gone through reciprocal, I have gone through Pythagorean, compound, half and double. I know the mindset that comes with it. Quotient is something a over b, reciprocal is 1 over a, Pythagorean has identity 1, compound is some a plus b, half is some a over 2, double is some 2a. So with these identities, which one do you think you have to use? You realize that I can only make use of the compound identity because of the formulation I have. So sine 30 plus 40, it says sine will take the first guy. Sine is not selfish, so it's purchased with the cos. Cos come and take the second 45. Plus should produce plus. Don't forget, we established that. Alright, so I come back and say, so now cos can take 30 and then the sine can take the next 45. And you can use calculators to punch this and then you get an answer, whether in degrees or in radians. Okay, so I have my answer on the slides, you can verify that. Now to the second question, again some informations are being given. Sine x is given, cos y is given, and there's another information. There's a second quadrant given. Let me use the red for emphasis. This is an extra information we can never neglect. Second quadrant. What is the question asking us to do? We are asked to find sine x plus y. So again, I ask myself, which of these identities can I use? Is it the compound? Is it the quotient? Is it the reciprocal? Is it the half or double? You would agree with me that this will be the compound identity as I've written there. It is one angle x plus the other angle y, so it is compound. Again, so what do? I have to write the expression for the compound of sine, and then I see what I can do. But wait, what do I have? I have sine x given as this. I have cos y given as this guy. So these are known. It means these are unknown. I need to find them And how do I do that? And this is where the other identities comes handy. By the Pythagoras theorem, why do I say Pythagoras theorem? By the Pythagorean identity, sine square x plus cos square x equal to 1. We know that. This is why I said it's common. And because I want cos x, I can make, by change of subject, I can make cos square x the subject, and I have that, and hence cos x become plus or minus of that. As simple as that. In the same way, if I want this y part, I can have this identity, sine square y plus cos square y equal to 1. By change of subject, I have sine y to be that. Change of subject, I have y to be that. So this is what I'm going to use. Let me say equation 1 and then equation 2. This is what I need. So when I come back to my expression, I already know sine x. It was given in the problem as, let me look at my slide, 3 on 5. Oh, 3 on 5. My cos y, it was given as negative 12 on 13. Plus, what do I get for cos x? What do I get for sine y? From the identity, cos x equal to plus or minus square root of 1 minus. Now you know that in trig, sine square x is the same as sine x all square. You should know that. So it means I have 3 square over 5 square. My handwriting is getting bad. I don't know why. 3 square over 5 square. If you use calculator to get this answer, I'll get plus or minus some answer. In the same way, my sine y becomes plus or minus square root of 1 minus 144 over 169 because of the square. Again, I'll get plus or minus some answer, which you have to use your calculator. Then the question becomes, which one do I use? Do I use a positive or the negatives? And this is where the second quadrant information becomes important. When we take the quadrant, the first quadrant, everything is positive. In the second quadrant, only sign is positive. In the third quadrant, only tan is positive. And in the fourth, only cos is positive. Since I'm in the second quadrant, it means that my cos will take a negative answer. The negative answer I get. No, that is not the right statement. The negative of the answer I had. And then my sign will take the positive of the answer I had. So you take note of it. If you go through this calculation, I think cos is giving us, let me write the answer for you. Cos is giving us plus or minus 4 on 5, plus or minus 4 over 5, and then sine is giving us plus or minus 5 over 13. So since I need to take the negative answer, it means I'm going to take negative 4 on 5, and then here I'm going to take positive 5 on 13. And so my cos x become negative 4 on 5, 5 on 13, and I can get my final answer. I hope it wasn't that complex. It is the use of the identities. Okay. Now let's look at the half and then double. That's the last thing to do. Again, these are not magic. They are ways to prove them, but we are going to use them as end users. One interesting thing I want you to take note is the double angles for cos 2a. It has three different identities, and they all have a purpose to play depending on how your expressions will look like. Another interesting under the double angle is a sine 2a. You can never forget this identity. And then the others are there. So let's quickly take examples of how to use these identities, since that is our interest here. In example 1, some information is given. I think my write-up is a bit large here. Sine A is 3 on 5, and I'm asked to find the value of sine 2A. Again, I ask myself, am I going to use quotient, through reciprocal, Pythagorean, compound, half, double? Where does 2A fall? Again, I told you quotient is something over something. Reciprocal is 1 over the thing. Pythagorean has its own component adding to 1. Everything sum up to 1. Compound is A plus B. Half is A over 2. Double is 2A. Where does this fall? Automatically, we realize that it is the double angle. This is how you get to know which of the identities to use. So I quickly go to my table or my cheat sheet and look for what sine 2A is, and that is the expression for sine 2A. Now I realize that I only have sine A answer, but I don't have cos A. So what can I do? I have to use an identity. So I went ahead and used the Pythagorean identity. It says sine square A plus cos square A equal to 1. And by change of subject, because I want cos A, I have to make cos A the subject. I have equation 2. And hence cos A becomes the square root of it. So this becomes 1 minus, again I told you in the trig, a square is the same as sine A all square. So I have 1 minus 3 on 5 all square. I don't know what this answer is, but I think I have already solved it. I had 4 on 5. So by substitution, sine 2A becomes 2 times 3 on 5, and then the cos A we had 4 on 5. That's the square root of 1 minus 9 on 25. You must use calculator to get this, and whatever answer you get is your sine 2A. As simple as that. The next example, example 2, it says use a half angle formula, evaluate sine 75. Again, I know you can use calculator, but let's go by the problem. This has given us exactly what to do. It says use a half angle, no stress. You're not going to think what identity am I going to use? No, it says use a half identity. Half means the angle must be over 2. But I asked to find sine 75. So I go and take my angle identity. I move to slide 14. I have equation 1 as the identity. Sine theta on 2 is given as plus or minus 1 minus cos A on 2. That is the identity. But I don't have 75 on 2. I have theta on 2. It means I must be able to rewrite this in terms of theta on 2. So this is what I do. Let me use the red for emphasis. I sine theta on 2 equal to 75 because I'm equating them. And the only way to get, I think the red is not necessary. The only way to get my theta on 2 is by change of subject, which I get 150. It means it's 150 on 2. 75 is 150 on 2. And I can employ equation 1. Wherever I see theta, it is no more 75 but 150 because I'm using the half angles. I'm not so sure if this is a bit confusing, but I believe when you take your time and then replay this lecture video, you should be fine. So the question is, I'm going to get plus or minus some answer. Do I use positive of the answer or I use negative of the answer? That's the question for the goals. But I realize that we have sine 75. If I use the quadrant form, 75 falls here. it means it's in the first quadrant and all are positive, so I wouldn't need the negative answer. I'll need a positive answer for this. So I think in my slide I didn't get the final. I said it will be 0.965 since it is in the first quadrant and all is positive, or all are positive. Okay, interestingly, aside the double and half angles, we can have higher identities. Higher identities means I can look for cos 3 theta, cos 5 theta, sine 6 theta. I can find a way to compute this by using the double angles. So realize that cos 4 theta, if example as what I have here, I can rewrite it as two compound identities, 2a plus 2a, and by the compound identity I have this guy here. Whatever happens next is some manipulations to be done, but because it's cos, the plus becomes what? Minus. This is the same, this is the same, so I can have a square of it. Now which identity would you use here? And that is up to you to figure them out. So that is the essence of the higher angle identities. So you can prove for sine 3a, you can also prove for cos 4a in terms of that. Okay, now to the last thing, that is a problem of the day. I think I've rushed through this lecture video. I feel like I have rushed through, but it is fine. We are in some biochemical lab, and we are looking at a reaction between two molecules. You know, the angle of their bonding affects the reaction rate, or how efficient these reactions are. It says the efficiency is given by some model. The model is written as what I have here, E equal to something. Now some terms are being defined. The term is alpha equal to a value, beta equal to another value. They are given. It says alpha is 40, so let me write it down, and then beta is 30 degrees. The question is to find the compound identity for E. This has given us a clue of what to do. Even if the compound identity wasn't stated, from the preamble given, you can tell where this is from. It is not from the quotient identity, neither from the double identity or half. It is from the compound identity. Now the next question is this resulting to the sine alpha plus b, or it is resulting to the cos alpha plus beta? But one thing I know is that the sine positive gives me positive, negative gives me negative. For cos, the positive gives me negative, negative gives me positive. And so from E, I realize that cos has nothing to do with my answers or my preamble. It means that E is sine alpha plus beta equal to whatever given. Sine alpha cos beta plus cos alpha sine beta, and that's the expression for E. So it means I'm looking for sine alpha is what? 40 plus 30, that is 70 degrees, using whatever is given, and that is simple. So sine 40, I've solved this problem to the end. Sine 30 plus cos 40 sine beta is 30. And so what answer do we get? Using a calculator, you can guess what this answer is. So sometimes I always tell you, you don't rush through the problem. You take your time, extract information, and then you realize how simple the question is for application. And this brings me to the end of my lecture video on trigonometries. kindly take some textbook and solve so many examples as you can. Okay, and that will help you. And to this, the next lecture, that is lecture 6, will be on polynomials, and we'll have 4 more to go under algebra. Bye.